Good morning, ladies and gentlemen. Today we're going to look at investments and loans, but representing them graphically. So representing the total value of the investment and loan as a graph over time. There's two ways to do this. One way is to think about the rule, and the other way is to think about a recursion relation. Let's start off with looking at the rule. And the calculator comes in very handy here. So here, the principal 3,000 invested at simple interest at 5% per annum. The rule for this is the value will be equal to 3,000. So it starts off at 3,000, and then what's added on is 5% of 3,000 every year. So 3,000 times 5 on 100 times t for the number of years. So let's look at that graphically. So we'll have 3,000 plus 3,000 times 0.05, which is the 5 on 100, times time, but here the x-axis is called x, so that's our time, in years. Enter. Now up here, we should put in maybe 6,000, because we would expect you there. That's simple interest growing at 5% per year, graphically. And note the line is straight. I might stretch this out even to 20 to go a little further. So that's looking 20 years into the future. Within about 20 years, it's worth $6,000. Let's look at the second one. It's slightly more difficult. So here, the principal is 2,900 and it's compounding monthly. So the value will be equal to 2,900. Now, because it increases by a percentage each month, it looks like this. 1, that retains its original value, and then to increase it by a percent, it's 5 on 12, that's percent each month, over 100, to the power of, now not just here, n, because t above is in years. So here, if that t there was just done years, it wouldn't fit on the same axis as the other one. Eventually we want to plot them both on the same axis. So what we'll do here is write 12t. Alright, and let's look at what that does on the graph. So we would do 2,900 multiplied by bracket 1 plus bracket 5 on 12, close bracket, over 100, close bracket, to the power of 12 times x. Alright, neat. See how the brown one is curving up. Compound interest grows by more interest each period, so it'll curve. And if we want to find where one overtakes the other, we go Menu, Analyze Graph, Intersection, below and above. Now my settings are a bit messed up, but that there is reading the number of years. 5.72 years in, that there is $3,860. I should change my significant figure settings. Alright. And if you wanted to, you could sketch that on here. Once again, if you're sketching a graph, we do expect you to include 2 points. The starting point is nice and easy, because you'd be starting at 3,000 and 2,900, clearly labelled points. Then sub in a value for t. So you might sub in t equals 3, and that will give you 2 points to sub for the graph on the y-axis. Let's consider a third option. Third option starts with nothing at the bank, so $0 principal. 5% compounding monthly, nice. And $100 deposit at the end of each month. When is C worth more than A or B? Now here, because there's a combination of geometric and linear, we can't just make a rule that graphs beautifully. Instead, we're going to have to do the recursion relations. So recursion, for here, for A, remember it was $3,000, so VO equals 3,000. And then to get from one to the next, we said Vn is equal to Vn plus 1. Sorry, Vn plus 1 is equal to Vn plus 5% of 3,000. So 5 on 100 times 3,000 which is probably $150. So you could, if you wanted to, replace all of that with $150, meaning it goes up by $150 each year. So that could easily be written as $150, but we'll leave it as that for now. The recursion relation for 2, well, VO is equal to 2,900. Vn plus 1 is equal to Vn times 1 plus 5 on 12 on 100. I know that looks like a date. What we're doing there is we are increasing it by 5, well, each month by that amount. And note this is monthly here, whereas this one is annual, which makes this problem really quite hard. So monthly, annual, and we've got to figure out a way to do that neatly. And eventually we want to graph all of these next to each other to see when C is greater than the other two. Alright, let's look at C. The initial value of C is 0. To get to Vn plus 1, we go Vn, and we multiply Vn by 5% each month. So we take this same portion here, and it goes up by that also. However, at the end of each month, we then add on $100. Right? So there are those 3 recursion relations, and this one is also working monthly. Right? To make this easier for us, you see how we've got 2 monthlies and 1 annual. And I doubt you'd have to do this in an exam, but worth looking at. How would we make this recursion relation from annual to monthly? The way we would do it is take this 5, because instead of going up by 5% of the original value, or of the value before, you would go up 5 on 12 of it. So it will no longer be 150, it'll be 1/12 of 150. So with simple interest, if it goes up 150 a year, it's equivalent to saying it goes up 1/12 of 150 each month. Right? So now we have the 3 recursion relations, and we've converted this one to monthly. Let's look at how we can graph that. Well, first of all, we want lists and spreadsheets. And this is going to be time. And we are going to do 1, 2, 3, etc. And these are months. And we want quite a few of them. Let's go out to, say, 100 months. So, a few. And then this here is, let's go with option A. And option A starts off with $3,000. And then to get to the next step in option A, we did the one above, and then we added on 5 on 12, 5 on 12 on 100 multiplied by 3,000. So in 1 month, it goes up $12.50. Let's take it down to the 12 months. That's how much it goes up over 12 months. So my mental arithmetic of saying 150 in my head was clearly wrong. And we should continue dragging this down. Oh no, sorry, there's the 150. My mental arithmetic wasn't wrong, it's just I remember that this is not 12 months, that's 11 months in, because that's V11, this is V12. So at the end of the year, it has gone up by 150, and we'll drag it down. All the way to 100, or past it, doesn't actually matter. Option B. Now, if you want to skip ahead, then you can see what's coming, great. Option B is the recursion. So it starts off with 2,900, and it goes up by 5% each time. 5% monthly though, so it's equal to the one above, multiplied by 1.1 plus 5 on 12 divided by 100, and that's what happens each time. Well, that's not right, is it? Oh, no, it is. Sorry. We're all good. Scroll it down. So it's going up by the monthly amount each time. And we can see down here, at some point, one is bigger than the other. No, no, no. It's getting closer. There. So between months 69 and 70, option B overtakes option A. Let's look at option C. And option C is the reason we had to use this recursion relation. Option C started off with no money. And then what happens with option C is we have the one above is increased by 5%, but monthly. So whatever a 12th or 5th percent is. That is 5 on 12, 1 to increase it, plus 5 divided by 12 on 100. Then, after it's been increased by 5%, we add on $100. Was it 100? $100. So at the end of the month, we have $100 in the account. That's because it's gone up by 5% of 0, or percentage of 0, and let's drag it down. Alright, so it overtakes the others really quite quickly, this option. It is higher than both of them by, not there yet, there, 33 months. If we explore that graphically, we can go here. We want time on our x-axis, and if we look at option A, we should see a straight line. Neat. Then we can add a y variable. Option B. Option B is the orange one. We can see it curving slightly. That's because it's compound interest. Option C will also curve because there is an interest component. Option C starts low and increases with a slight curve. Pretty cool, huh? Alright, sorry that went for a while, but I think it's important you should be able to use the rule to model and create graphs from it, and then use the recursion relation to get the more complicated models and use it in terms of months, years, etc. Alright, thank you very much.